Hello everyone. In this video, we will be discussing distributed consensus algorithms, which are necessary for maintaining consistency in a distributed system. This technology or the set of algorithms is also used in blockchains. Let's get started. Consider a distributed system which we want to be having strong consistency. But due to some faults, maybe network delays or failures, nodes are having different data for same record. We know that many of the distributed systems are high availability partition tolerant system. And as per CAP theorem, we cannot have availability and strong consistency at the same time. So we have to trade off between high availability and strong consistency. But we still want in some of the systems that they should have strong consistency. But there are some faults in the system, for example, network delays, replication lag, or failures, due to which different nodes can have different data for same record, at least for some time, which is not in accordance with the strong consistency principle, where at any given moment, all the nodes should agree on the same value or the same thing. Which value should we consider in this case? So let's say in this image, you see server 1 is saying a value of 10, server 2 is saying a value of 11, and server 3 is saying that the value is 14. Now, which state should you consider? All nodes must agree on a single value of this data, which is known as consensus. Let us understand this. On LinkedIn, you posted something. So there is a post. After 30 minutes, you realize that there was a typo and you corrected that typo. You see, there are three data centers. Let's say one is in US, one is in India, one is in Singapore. Let's say the request went to India server and this is having up to date data. That means it is having updated data too. But the US location and the Singapore location are still having older version. Now in that case, which data should be shown to the user? How do we know which is the latest data? So all nodes must agree on a single value of this data until all the servers have the same data. This problem of agreeing is known as consensus. And we will be discussing consensus algorithms in this video. If you have not subscribed to the channel, please subscribe to the channel so that you will get more such videos in the future. You will be notified whenever I upload any video on Java, AI, interviews, distributed systems, microservices, and system design. Let's move ahead. Distributed consensus is hence a fundamental primitive for constructing fault-tolerant, strongly consistent distributed systems. There are two major algorithms for consensus. First one is Raft, which is a modern approach. Let's discuss this. Raft as a consensus algorithm is used by CockroachDB, Neo4j, and etcd. These are the databases. For example, Neo4j is a graph NoSQL database. Raft depends on logs. Every operation is logged. When any inconsistency is found, logs are used. So this is essentially making all nodes agree on a particular version of logs. Since every event, everything, every operation is logged, so this becomes the problem of essentially making all nodes agree on a particular version of log. Writes happen using leader. But how do we know if a leader is dead? Since leader is now a single point of failure and all writes are happening because of the leader, how do we know if leader is dead? Because if the leader is dead, we cannot do any writes to the system. So leader sends heartbeat to each follower node. This heartbeat is nothing but is alive message. A simple packet which is sent to the followers from the leader that, hey, I am alive. Hey, I am alive. Each follower node maintains a random timeout in which if the leader's heartbeat is not received, it considers leader as dead. For example, you see, this is the leader and there are 4 followers. The follower 1 is maintaining a timeout of 100 milliseconds. So if leaders is alive message, the heartbeat does not reach follower 1 in 100 milliseconds, it will say that leader might be dead, but it will keep retrying. That means it will wait for 3 such cycles. For example, in this case, 300 milliseconds. If it sees that still no heartbeat is there, it will declare from its side that I have not got any heartbeat from leader, and hence, due to my timeout, after 3 retries, I am saying that leader is dead. But for the second follower, it will be 330 millisecond. For follower 3, it will be again 300 milliseconds. And for follower 4, it will be 360 milliseconds. So, whichever follower first detects the leader as dead becomes the candidate for the next leader and asks other followers to vote for it. In this image, you see follower 1 and follower 3 will first detect that leader is dead. Because the leader is actually down, it won't be able to send the heartbeat. So after 300 milliseconds, follower 1 say that the leader is dead according to me. Follower 3 will also say that leader is dead according to me. After 30 more milliseconds, follower 2 will declare leader is dead. And after 60 more milliseconds, the follower 4 will declare the leader is dead after follower 1 and follower 3. So follower 1 and follower 3 first detect that leader is dead, and hence both become the candidates for becoming the next leader. So we have candidate 1 and candidate 2. And they will ask the other followers to vote for them so that they can become the leader. So say log length at node 1 is 100. 100 log is there. 100 logs are there. The length of the logs at follower 1 is 100. And at node 3 it is 101. So which one is the latest one according to you? That means actually that node 3 is more up to date because it is having more logs as compared to node 1. And hence node 3 will become the new leader. To synchronize the logs, leader relies on two-phase commit. Two-phase commit we have discussed in one of our previous videos. If you have not watched that, please go to the description of the video and you will find the link. Where it leader sees if at least half of the nodes are able to append. So in the two-phase commit, we had seen there are two phases before doing the commit. First is the voting phase and second is the committing phase. So first it sees that at least half of the nodes are able to append. If yes, it commits and tells every node to commit as well. Because if half of the nodes are able to append, that means n by 2. If n is the number of nodes, n by 2 is able to append. And 1 is the leader itself. So you have a quorum here, a majority nodes who are able to append. So it commits and tells every node to commit as well. And in this way, consensus is reached because more than half of the nodes, greater than 50% of nodes, are able to commit the new data. So in this diagram, you see y is equals to 9 value arrives. So you see, this was the length. Every node, leader, follower 1 and follower 2, they are having a length of 2 for the logs. And y is equals to 9 arrives. It asks the other nodes if they can append. So it is asking. This is the voting phase. Once it receives the response from more than half of the nodes, it commits and asks the other nodes to commit as well. So this length is incremented and now every node is having the same length of the log. Now suppose a node was down for some time and meanwhile new log entries were committed. In that scenario, when node comes back, it will ask the leader for log entries it missed. Only after this synchronization of logs is done, it will start appending incoming log entries. So if a node was down for some time, when it comes up, it will ask the leader, hey, are there any new logs? If so, first give me those so that once replication is done, once I'm done with catching up, I will come and start ingesting or appending more incoming log entries. So Raft can be used for any finite state machine. Finite state machine we already know, where we have n number of states and there is a definite constraint of which state can go to which state. This you might have studied in your compiler design or while studying the finite state automaton. If you are not aware of that, please let me know and I will try to cover this up. A good design pattern for this is the state design pattern, which can accurately represent this finite state machine. Let's come to the second approach, which is the Paxos, and this is the classical approach. It is used by Cassandra, AWS, ECS, and Neo4j. Similar to Raft, Paxos also guarantees that leaders' logs are containing all the previous commits. Similar to Raft, Paxos also assumes partially synchronous crash recovery systems. But how does it differ from Raft? In Raft, a node can vote for a candidate if candidate is greater than or equal to node in terms of number of log entries. So for example, let's say follower 1 was having a log entry of length 100, follower 2 was having log entry of 99, and follower 4 was having log entry of 104. Just a scenario. Then follower 2 can vote for follower 1 and follower 4 because it is having lesser number of log entries. But follower 4 cannot vote for follower 1 because follower 4 is ahead of follower 1. Follower 1 can vote for only follower 4. It cannot vote for follower 2 for the same reason that the length of the logs at follower 1 is greater than the length of the logs at follower 2. But in Paxos, any node can vote for any node, and hence, once it becomes leader, it synchronizes the logs. So Raft is more efficient in leader election because of the voting mechanism. Now, which one we should use? We discussed that Raft and Paxos are much similar approaches of consensus, but which one we should use? Paxos is the classical solution for distributed consensus. Raft is comparatively new. Paxos is somewhat harder to understand, but Raft is comparatively easy to understand. Paxos is less efficient for leader election because an outdated node can also become the leader. Raft is equal to multi-Paxos and is still as efficient as Paxos. In short, both Paxos and Raft take a very similar approach to distributed consensus, differing only in their approach to leader election. So in this video, we discussed distributed consensus algorithms, how they ensure consistency for distributed data. They are also used in blockchains. We took a couple of examples and discussed the approaches like Raft and Paxos. In an upcoming video, we will be discussing two generals problem, FLP impossibility. So if you want to stay tuned, please subscribe to the channel. If you like this video, please consider sharing the video as well. If you have any topic in mind which you are having a difficulty to understand, please feel free to comment and I will cover that topic in an upcoming video. Thank you so much.